welcome back to Gaga Outdoors. Today we are at the MagLab. The Magnetic Lab.
The National High Magnetic Field Laboratory, the world's largest magnet.
Guys, look, they even have a playset.
All right, we're late for the tour. Let's go.
Paperclip magnet, right? And that's just because the way the tiny particles called electrons are lined up in the magnet and they're attracted to this metal. But our electromagnets are different than that. You can turn them on and off because we make them a magnet by running electricity through a wire. Anytime you run electricity through a wire, you guys may remember this was an experiment in grade school. You run electricity, you attach a wire to a battery and you coil it up and you put a nail inside the wire and it turns it into an electromagnet, and you can pick up paper clips when the wire is attached to the battery, right? And that's essentially how our magnets work. They're giant versions of that. They're electromagnets and they're just scaled up. And instead of using a wire, we use something called this, which is a metal disc known as a bitter disc.
A what disc?
Bitter, B-I-T-T-E-R, named after Francis Bitter, who was at MIT in Massachusetts, and he invented this. Rather than using wire, run electricity through these discs. These discs are made of copper or copper and silver. And you run electricity through these discs and it creates a magnetic field in the middle. But not just one disc, many, many discs stacked up in a giant helix like a big spiral staircase or a slinky, and it's all pressed together. So you have hundreds and hundreds of discs all stacked up with insulators in between. You see an example of it in several places here, how the discs are stacked and then they're pressed together really tight. And when you do that, it creates the high magnetic field in the middle of the magnet. And then, in addition to that, you nest the discs. So you have a tiny one in the middle, and you have a bigger one. You see them here laid out on the table. You have a bigger one wrapped around that, and another big one. And these are the magnet coils. And they all create that high magnetic field right in the middle of the magnet, which is called the core, or the bore of the magnet. And that's where we place a sample to study in a high magnetic field. And we take a probe, which is just a fancy word for a scientific stick, and it has the sample on the end of it, and we take it and we put it down into the middle of that magnet to see what's going on with that material when it's in a high magnetic field. So when you put electricity through metal, what do you guys think happens? What do you think happens with electricity running through metal? What might happen?
Warms up.
It sure does, like your toaster, except a lot more. So when it warms up, we have to cool the magnet with a lot of water because we're pumping a lot of electricity through it. So that's what these slots are in the disc. At the same time that you're running electricity through it, you're running water through it. A lot of water under high pressure. The water is moving at about 45 miles an hour. And so about 2,000 to 4,000 gallons of water every minute is rushing through the magnet to keep it cool. And you might think, well, water conducts electricity, right? Does water conduct electricity?
Pure water doesn't.
Pure water does not. And so that's why we use pure water that's called deionized water. So everything is taken out except pure hydrogen and oxygen bonded. And so that's the deionized water that is pumped through our magnets to keep them cool while they're operating. So that's the bitter disc, and these are the slots for cooling. Now originally the discs designed by Francis Bitter were a little bit different. You see one of them right here. They had just holes for cooling water. And so the new disc, you see the difference with the slots instead of holes? This was developed here at the MagLab. It's called the Florida Bitter disc, as opposed to the old-fashioned bitter disc. The Florida Bitter disc, by staggered slots for cooling water, they were able to make the magnets up to 40% more efficient by changing the design of the cooling slots on the disc. So this is your Florida Bitter disc. You'll see these all over the lab. People like to use the old discs that were used in magnets and are no longer being used for artwork. So you'll see artwork, bitter disc artwork and decorations all over the lab, such as this one right here.
Oh, that's cool.
And those Olympic rings over there. And some other ones throughout here.
Do Do y'all give those out to the public
We
to
do.
use for
We do have
artwork?
those.
Oh,
We do give those out. to the
that's
public.
cool.
And so the bottom line on the magnets is you see this giant coil right over here. This is the outer coil of one of our strongest magnets right here. And there's 1,000 or more of those discs all stacked together. And you see these are the layers of that magnet right here on this table where I'm standing. These are all the different coils that are stacked together to create that giant electromagnet. And we also have something called superconducting magnets. Those use a thin tape that looks like this. Looks like a piece of spaghetti. I mean, fettuccine, right? You guys want to look at that and pass it around? And there's a tiny piece of material in the middle of that can carry electricity without any resistance, but it has to be kept super cold in order to do that. So it doesn't create heat buildup, and the electricity can keep running through that magnet with insulation in between each layer. So the magnets take a long time to put together, but they're unique in the world. These are the strongest magnets ever made. Nothing's been made like them ever. So that's why it's a long process to do that. Yes, sir.
Is the Earth a giant magnet?
Yes, the Earth is a giant magnet. Yeah, the Earth, we're all standing in the Earth's magnetic field right now. And in fact, the Earth's magnetic field is strong enough that it pushes away some certain cosmic rays and waves that are coming to us that could be harmful to us. So the Earth's magnetic field actually protects us from some of the nasty stuff that's in outer space. So the Earth is a giant magnet. Yes, ma'am?
The water that's used for cooling, the ionized, once it goes through, doesn't it heat up? And do you recycle that water back through?
Yes, we do. And we'll learn more about that in our control room a little bit later on
It
the
gets
tour.
cooled, but does it need to be de-ionized?
Again, yes. It picks up particles when it's running through the pipes and magnets. So it has to be deionized. Just like anything else mechanical. No, it's not magnetic. Just like anything else, they wear out over time. You're running all that electricity and water through them. Get some that are better. There you go, guys. So you have a little souvenir from the MagLab.
Thank you.
Everybody get one? So this is the control room for the MagLab. This is where technicians are monitoring the power and the water and the other infrastructure that's being used to operate our magnets. This room is staffed about 17 hours a day normally, Monday through Friday, to operate our magnets because we have a schedule that goes from early morning until late evening because there's demand for magnet time from researchers from around the world. So we have our own substation from the city of Tallahassee. A gentleman asked about that from the other group. We have our own substation. We use about 8% of the entire city of Tallahassee's power capacity. About 8%. That's 56 megawatts of power. 1 megawatt can power about 500 homes. So you're talking about 28,000 homes worth of power that's being used to operate our magnets. And that's only enough to operate 2 or 3 of our most powerful magnets at the same time because they're taking in 30 megawatts of power into one magnet. So the power bill here at the MagLab, I know it's summer, it's hot, you probably are paying a lot for the power bill right now and you're upset about it, but here at the MagLab, the power bill is about $250,000 to $500,000 a month. So this is one of the reasons that the National Science Foundation and the state of Florida supports the research and the infrastructure being done here because nobody else could afford the kind of capacity needed to conduct the research. So you see how the power comes in from the substation. There's a power yard, transformers to go from to lower the voltage, increase the current, and then you want to change from alternating current, which is what the power supply is, where it's flipping back and forth, to a direct current. So it's a direct current so that it'll run the magnet nice and smoothly. Then it goes through filtering to get to the magnet. Up here you see how the water system works. We have the cooling tower out back. We have chilled water tanks, a series of chillers. It's all back here behind the control room. And that's what chills the water and pumps it through those magnets at 2,000 to 4,000 gallons per minute again. So the water tanks out back can hold about 4 million gallons of water that's available for cooling those magnets. And it's a closed loop system of deionized water that's running through the magnets, chilled water that's beating that to cool it off, and then another loop of water that's taking that warmer water and taking it outside to be released into the atmosphere and cool off the whole system. They're being concentrated onto a tiny space at the center of the magnet. So the fringe field is very small and it dissipates very quickly, so it doesn't leave the building. So there's no evidence that it does anything to affect the weather. Yes, sir.
How does the water heat up when it goes through it?
Well, there's heat energy coming from the magnet. Remember, you're pumping all that electricity through metal, so it's heating up. And the water is cold, so that heat is going from the magnet to the water, and then the water is being looped out, and it's taking that heat energy away, and it's transferring it to another water loop, and then it's going out to the atmosphere. Yes?
Has it ever affected anybody's credit card or cell phone?
If you would get extremely close to a magnet while it's at a high magnetic field, it could erase your credit card, it could damage your phone, it could affect something like a pacemaker. We're not going to be in those fields. And there are precautions that are taken to make sure that that's
Not
okay.
happened to anyone here?
Not that I know of, no. Produces a 45 Tesla magnetic field. Remember, that's about 1,000,000 times stronger than the Earth's. It could pick up a bunch of buses, right? It could pick up a ship. It's extremely powerful. But the magnetic field is not going out into the atmosphere. It's focused on that bore at the center of the magnet and is only 32 millimeters around the bore, which is like about 1.5 inches, 2 inches. So that's the...
3.2 centimeters, right?
What's that?
3.2 centimeters.
3.2 centimeters. Very good, sir. So that's where the magnetic field is focused, and that's where the sample is placed to be studied. So this magnet it's 22 feet from top to bottom. All this stuff down here at eye level and up to that first platform, that is all cooling water and helium piping that's going there, mostly cooling water. And then up at that gray barrel, that's where the actual magnet is located. And that gray barrel is holding a vat of helium, which is cooling the outside of the magnet. So this is a hybrid magnet. It has a superconducting magnet on the outside. So that's made of that wire that carries electricity without resistance, but it has to be kept in liquid helium at the temperature of outer space at about minus 456 degrees. So that's on the outside, and then on the inside you have that resistive magnet made of those bitter plates that you each have now, made of those, small ones, bigger ones, bigger ones, bigger ones. So it's about this big around, and it's made of those, and it's being cooled with water and electricity being pumped into it as well. So you have those two magnets wrapped around each other to create the 45 Tesla highest magnetic field. This magnet is, like we said, about 35 tons, so it weighs as much as a bunch of cars or elephants. And there's a platform, you go up these stairs over here to the platform at the top, and that's where we place the sample into the magnet from way up there. And there's also a computer control station to operate the magnet up there. Does anybody have questions about the 45 Tesla hybrid magnet? And as we were coming down the hall, you see all the red numbers, the red circles with the yellow numbers in them. Those are all what we call the magnet cells. This is cell 15 for the hybrid. And those all have a different magnet of a different strength that are being used for different research purposes and being reserved by researchers. Yes, guys?
How did they make the magnet?
How did they make the magnet? Well, it took a long time. It probably was about 5 to 10 years with the planning and development and building of the magnet, and it cost a lot of money too to put it together too. And nothing like this had ever been done before, so they had to test it over and over again to make sure they were doing it right. And they made mistakes. They fixed the mistakes. They kept going, and they made it over time. And a lot of smart people put their heads together to figure out a plan to make the magnet.
Is it was really, really big, would you need a lot of water to cool it down?
It does. It uses a lot of water. This one uses 4,000 gallons of water every minute when it's operating. So it costs a lot of money, and a lot of water and electricity just to operate it every hour, for instance.
Why did it require 500 pounds of pressure for the cooler water?
The water just to push it through as quickly as possible to keep the cooling flowing. Through those slots, yeah. So what we're going to do is we're going to go back up this way. We'll take a peek into one of the other magnet cells just to give you guys a sense of what those look like. They're a little bit smaller than this. And then we'll head back to the other side of the building to learn about our MRI magnets and our biology and chemistry related research. Here, guys. That board that has numbers on it back up there at the top, what does it say? Come on over here and get that. What does that say right there? You see that? It's 5.5. That's 5.5 Tesla. This magnet is on right now. You guys feel that? No, I didn't think so. The magnetic field is in there. So this is cell 6. This is a 41.5 Tesla magnet. This is all resistive, so it's made of those big bitter discs. And I wanted to show you this one because we were standing next to that big coil, that giant piece of copper coil that was in the magnet factory. That was the outer coil of this magnet right here that you see straight ahead behind the plexiglass walls. So the magnet is straight ahead, sort of at eye level, and up above the platform, that silver barrel is what's called a cryostat, and that's usually using liquid nitrogen is cooling the sample because they want to slow down the particles moving around in the sample by cooling it before they study it in the high magnetic field. So then above the barrel you see the probe that holds the sample at the end of it. The probe goes way up in the air there, and it has all those things connected to it, and those are different ways of monitoring, connecting measurements to the sample at the other end of the probe. The probes are laid out on this table here. You see one of them laying right here on this table pointing towards us. The end towards us is where the sample goes, and the other end is what sticks up in the air and has all the instrumentation attached to the end of the probe. So this magnet is on right now, but it looks like they're cycling down on the magnet. It's now at 5.3 Tesla, so it takes a while to go up and down on the magnet. This magnet can go to 41.5, so they may have gone up higher, and now they're coming back down as they're doing their research. I talked to these guys earlier. They're from Ohio State University, here conducting research at the MagLab. Again, folks from all over the country, all over the world come here to do their research. So that is your typical magnet cell right there, and you see the wooden chair up at the top of the magnet. Why do you think the chair is wooden?
Magnetic.
So that it doesn't get, if you had a metal chair, it would get pulled into that magnetic field if it were that close to the magnet, so they have to be careful about that. So there's a lot of wooden chairs around here for good reason. But they have the fringe field, as they call it, is marked on the floor here, so that they make sure that they're not getting too close to the magnet if they have metal on them, or if there are other reasons that they can't be close to the magnet.
How do you put a sample on the end of that thing?
You use the microscopes right here. Place it, it's in like a little holder at the end of the probe.
Glued on or?
It's placed in like a small holder. It's different, all kinds of different probes and styles that they use.
Metal.
Well, they can be metal as long as they're not magnetic metal. Metal that's not attracted to magnets, like copper or brass or others. Yes, sir.
As far as the research here, is there a fee for coming?
The research is free as long as you publish the results. And that's another reason that the National Science Foundation and the state of Florida support the lab in the interest of science for improving humanity, and that's why the research, there's no fee for the research as long as you publish it for everybody.
So do they have to go through like a rigid approval process?
There's a process where they submit their research proposal to a scientific committee. It's made of outside researchers and inside scientists, and they have a system where they rank the research proposals, and then those are sorted through and those that are approved are given magnet time, hours in the magnet cells, and there's more demand than there is magnet time available.
Is the sample here biological?
In this case, it's probably some kind of new material that they're studying, and they're looking at this new material for maybe for something for quantum computing or new memory storage or a new battery, a new computer chip, those kinds of things that they're looking at. That's what goes on mostly in this facility that we've just been walking through, and on the other side of the building is where they're doing more biology and chemistry that we'll talk about over there. Yes?
Can you ever transport the magnets? And if so, what would it take?
You can. These are built in these places, and they're heavy and they're bulky, and they have all this infrastructure supporting them, so you really couldn't transport the
So
magnets.
it's like built around the magnet.
Because of all the power and the water and all that stuff, the magnet is basically built in place in this facility. Yes.
What's some of the applications for a laser in this?
The laser, so when they have a material in a high magnetic field, there's all kinds of things that they do to try to sort of stimulate the material or look at or see what's going on with those tiny particles, you know, electrons and protons and everything and how they're moving. So in addition to putting it in a high magnetic field, which can help them look at the material, they'll cool it down to see how the particles slow down, and they'll shoot it with lasers to see what that does to the particles too, because photons, you know, light is an electromagnetic wave, right? So by shooting lasers at something, you can see how the particles react to that as well.
I think that's the water.
Okay, what do you guys see over there?
Can I see the
What does that look like?
I see someone right there.
You see somebody working down there?
Yeah, me too.
Yeah.
I see somebody sleeping up.
Somebody's sleeping. Uh-oh.
Oh, watching TikTok.
Well, it's Wednesday. They're getting
Is this what a water is?
This is what we like to call the world's strongest MRI, magnetic resonance imaging machine.
What's an MRI?
An MRI is a powerful magnet, and it's used to take pictures inside your body. And so this MRI can't do people, though. Its hole in the middle is only about the size of a softball. So it does animals. So they use this MRI to look at rodents and birds and mice and other small animals to do preclinical medical research. This MRI is 21 Tesla strong. A hospital MRI, if you'll recall, is about 1.5 Tesla. So this is extremely more powerful than a hospital MRI. So it's able to get much higher resolution images inside of the living creature, in this case a rodent or a bird. And it's also able to see more things. A regular MRI that you have at the hospital is looking at inside your body by imaging water. It's actually looking at the hydrogen in water inside your body. This MRI, because it's such a higher magnetic field, can not only see hydrogen, it can see oxygen, it can see sodium, it can see phosphorus, and several elements inside the body. So it can take a look at how diseases are playing out, how medications are working, how cancers are affecting, how sodium is moving through the body. So this is used for research in terms of Alzheimer's and stroke. It's used for research on developing new lithium batteries because it can see lithium as well. So this is used for a lot of medical research here at the MagLab. You see that it cost $16 million to build, and it's 15.5 feet tall. And this magnet, the giant white tank, is holding liquid helium because this is an all superconducting magnet. So remember, that's the wire that you put electricity into it, and it can run and run and run without building up heat as long as it's kept cold in liquid helium. So this magnet is unplugged, and it's been running ever since. As long as it's in that tank of liquid helium, it's just being kept cold, and they don't have to pump electricity into it. This magnet, something different about it is they put the probe in from the bottom. So you see they go down those stairs there and put the probe in from the bottom. And you see a set of the probes along the right-hand side wall here. They're shorter, they're stubbier, and they're broader, of course, because you're putting something. You can put something fairly large, like a little animal, inside the probe. So the probes are along the right-hand wall over there. And so This magnet is being used for all that health research. You also see down here they have a metal detector to make sure nobody's getting too close to the magnet with metal on, since the magnet is always on. And they have the rings on the floor showing the magnetic field as you move away from the magnet to make sure people aren't going too close with something metal in their pocket or on them.
What happens if they did?
Well, that metal would be drawn toward the magnet, and it could
I mean, it
fly
fell through your
across the
pants,
room.
or, I mean,
It probably wouldn't rip through your pants, but it would be pretty tremendous force. It could fly across the room. It could hurt somebody. It could damage the magnet, the housing, something like that. And if it's a big piece of equipment that's metal, it could be extremely dangerous.
So the magnet is supercharged. It's always going.
Superconducting, yes.
Superconducting, and the helium is
Yes.
always cool. Do you have to? How do you keep the heat? Does the helium ever heat up or warm up?
The helium does. The helium boils off, and then we recycle the helium. The MagLab recycles about 90 to 95% of its helium. It collects the helium gas, and then it reliquefies the helium. And helium is a finite and expensive resource, so that's an important part of the program that they've developed, is to recycle as much helium as possible to cut down on the expenses. But yeah, the helium it warms up, of course, and it boils off. So you're constantly refreshing the helium. Yes?
Could you use a magnet like this to do some sort of ground penetrating radar mapping?
I don't think so. But I mean, radar would be the way you would want to do that.
But I was saying, like,
Radar,
version of that.
which is an electromagnetic wave, is a radar too. So it's all kind of related, because electromagnetism, which is sort of both sides of electricity and magnetism, they're both always related. So, yes, sir. Yeah.
What would happen if you did have a big piece of metal equipment and
But it could get pulled. It could get pulled to the magnet, so you have to be careful. You don't want anything metal to be too close to the magnet. Yeah, just to be safe. So there's a lot of safety protocols that everybody has to take when they're working around these high magnetic fields.
which one is the magnet?
The magnet is inside that big white kettle drum thing there, right there. So that's a big bath of liquid helium. That's super cold liquid, and it's inside there to keep the magnet cool so that it keeps running.
Is that what the other metal vats are running the?
The other vats are either liquid nitrogen or liquid helium, and those are often used to cool samples,
Okay.
as well as cooling magnets. And when the animal comes out, the high magnetic fields may affect its.
Put it on the rail, please.
People.
But other than
Oh,
that,
they're working in there? Don't put your hands on the glass either.
so guys, we're going to be looking over this way. This is our last stop. This is what we call yeah, there's people working down there. This is our ion cyclotron resonance facility. It's a mouthful, but I like to call it the CSI of the MagLab. CSI, you ever watched that show where they investigate crimes and stuff? So this area, they're able to take liquids, complex liquids, and put them in a high magnetic field and sort out all of the different unique molecules within that liquid. So for instance, a drop of petroleum can have 100,000 different unique molecules that are making it up, different chemical formulas for all those different pieces. And this can sort out every single one of those and figure out what's in a substance, essentially. So it's been used to analyze petroleum, analyze groundwater, analyze fracking fluids. They've done a lot of environmental research here. Asphalt runoff, you see some of them listed here. Microplastics, forever chemicals. Have you guys heard of forever chemicals that are in our environment? So they can spot those forever chemicals and fingerprint them and figure out where they are in our environment, which ones are out there. There's a lot of formulas that we don't even know are out in our environment. They've done some cool research here on meteorites. They've looked at what's in a meteorite, what organic matter is inside a meteorite that came from outer space, and what it means about the makeup of our solar system and our universe. They also looked at lunar soil recently to look at what organic material is inside the dirt from the moon, how it compares to what's on Earth, and how it may inform how the solar system was formed. Yes?
Do you currently have those samples still?
The lunar samples?
Yeah.
I think they're here, but you can't have them. They came from NASA, and they have strict security protocols regarding those samples. They have to be kept in a locked safe, and only one scientist knows the code to the safe. And the safe has to be in a locked room, and of course the room is in this locked building, and all that kind of stuff. And they're really tiny bits of lunar soil, but they came from the moon 50 plus years ago on the Apollo missions. And the technology to analyze them has come a long way since they were brought back. So they were recently sent here to take a fresh look at what's in them. Yes?
What is an meteorite?
What is in a meteorite? It's as complex in terms of the materials inside it. It's as complex as anything that's ever been seen on the Earth is in a meteorite as well. So isn't that amazing?
So it's kind of like a magnet?
No, it's not like a magnet. It's like a rock that has a lot of different pieces in it. It's like a puzzle. All these pieces put together to form this rock. Yes?
Like crystals?
How did they make the meteorite like fly into Earth?
Well, it came here on its own. It flew and it landed on Earth, and they got a sample of it. And then they brought it here and they put it inside the magnet to see what was in it. And they basically, when they put it in these machines, they're basically weighing it. And by weighing it, they can figure out what each little molecule is made of, because they all weigh just a little bit different, whether they're made up of nitrogen or oxygen or carbon or hydrogen, all these different component parts. And then they can figure out what those things are made of. It's a really delicate process, but it's really amazing what they can figure out. If you think about it, if we all weighed the same amount, say we all weighed 100 pounds, we stepped on a scale and they weighed us, and then we stepped off, and then one of us cut a small piece of our hair off, and we all stepped back on the scale, they could figure out that difference in weight and figure out which one of us had cut the hair off. That's the kind of precision measuring they're able to do here with this ion cyclotron resonance. And basically that's how they're weighing molecules, and every molecule is slightly different weight, and that's how they're able to pinpoint that forever chemical that's in this material, or they're able to pinpoint what's in this petroleum that makes it less efficient to burn or more polluting, or how do we develop a biofuel that's going to burn like petroleum but we can make it from renewable materials. Those are the kinds of research areas that they're working on here.
Is the budgeting for
Sorry?
the budgeting, is that tied directly to FSU, or is it a national thing?
We're funded in part by the National Science Foundation. That's for our user program for researchers from around the country to come here. And then the state of Florida also funds us. So we have those two funding sources.
So
and we also get a lot of grants from other places like the National Institutes of Health or the Department of Energy, Department of Defense, other places.
So a lot of the people working here, are they students or permanent employees?
There's a lot of students, but there's many permanent employees as well we're technically Florida State University employees. Okay. Yeah. So we're under the umbrella of the university and the Office of Research at the university as well. But we also have that funding source from the federal government as well. So.
Okay, well, when are you going to get this young man an application?
Well, we'll get all these guys applications. Each one of you.
Y'all gonna work here?
Keep us in touch. Keep in touch, and we'll get you on board. We have school tours. We have internship programs. We got all kinds of things that we can get you guys excited about science. And for those of you who are in the Tallahassee area or not too far away, we do have our open house every year, the last Saturday in February, which is a lot of fun because they do about 100 different science demonstrations all over the lab, and you meet all the scientists and see all kinds of stuff that you don't get to see on a regular tour. Yes?
Do you have the MagLab fridge magnet?
Yeah, somewhere.
Everyone has one but me.
Which one? What does that look like?
It's like the rectangle and it says MagLab on it.
Oh yeah, I might be able to get you one of those before you leave.
So working here, could you make a good living?
Oh yes.
Yeah.
Yeah, we have a lot of people who do well working here. Yeah.
We wanted to come see because their daddy is a surveyor and got to survey the magnet shut down the magnet and survey the area. So they thought that was so cool.
That is cool. Well, I'm
Yeah.
glad you guys came. That's exciting.
Our dad is a surveyor.
That's a cool job. Yeah. So we're gonna head back the way we came over here on the second floor, and then you guys can take the stairs to.
Welcome back to Gaga Outdoors. We just finished the tour of the MagLab.
What'd y'all think?
We loved it. 21.
21.
We loved it.
Oh, you loved it. What was your favorite part? Hands off. Stop. What was your favorite part?
My favorite part was getting all the souvenirs.
I can't hear you. Come out this way.
My favorite part was getting all the souvenirs.
The souvenirs? What'd y'all get?
Stickers, magnet, and some metal things. Can I take
Bitters.
this off?
Yes. What was your favorite part?
My favorite part was getting the stickers.
Oh, the stickers too? Yeah, this was really cool. They built this back when I was in like middle school. I haven't been here since middle school. That was a fun tour.
Can I put this on?
Yeah, go for it. And then Jackson got to shut down the whole magnet to survey it. So that's pretty cool. Would y'all want to come here again?
No.
Yes? No? Well, maybe we'll come back whenever they do their end of the month when they have all the scientists and activities.
Okay, guys. All right. Now we just finished the tour of the MagLab. Now, thank you for joining us today on Gaga Outdoors. Peace.